Assalamu alaikum. Assalamu alaikum. My name is Rimsha Timotheus and I am from BSPT and my course name is PC1 Principles of Chemistry 1, and today the topic of my presentation is colored flame production, chemistry, theory and the materials details. Colored flames. In the beginning, a question arises in our mind that how can we get these colored flames? And the answer is that the colors of a flame are caused by the bits of wax molecules that did not get completely reactive. We did flame test, and in these tests, we introduced a metal or any compound or material to heat. We heat them. Then, when we heat them, the molecules in it start to react. But there are some of the reactants, some of the atoms, or we can say that any molecules that cannot be react completely, and they are the main reason of the colored flames. These unreacted molecules glow a certain color when they get to be a certain temperature, since different parts of the flame have different temperatures. These bits of wax molecules make those areas of the flame glow with different colors. Now, how they are produced? The colors that we observe during the flame test is the result of the excitement of the electrons caused by the increased temperature. When we heated any element, any material, any metal, we give them temperature, and these increased temperature cause the excitement of the electrons of the metals to jump from the ground state to their higher energy level. We give them energy in the form of the increased temperature, and these temperature cause the electrons to be excited. And in this way, the atoms go from their ground state to a higher energy level, and in this way, colored flames are produced. Further about this, I will tell you later. Now, some of the examples are that copper 1 emits blue light during the flame test, while the copper 2 emits green light. And what is the purpose of this? Because each element has an exactly definite line emission spectrum, scientists are able to identify them by the color of flame they produce. It means to say that each element has different emission of spectrum. They emit different types of wavelengths of light. And in this way, they produce color flame which are also different. And in this way, the scientists are able to identify them. For example, copper produces a blue flame, lithium and strontium are red flame, calcium and orange flame, sodium are yellow flame, and the barium are green flame. In other words, we can say that if we obtain any metal or material and we do not know about its chemical composition or anything, even though we did not know his name, that which metal is this, and in this way we can do its flame test, and in this way which type of color we obtained during the flame test can identify, and we can able to know that which element or which metal is it. Now, what is the chemistry behind the colored flames? The chemistry behind the colored flames are this. Many ions of metals and non-metals turn flame into different colors. This is because when heated, atoms move when excited state. The same thing I have told you before, that when we heated a metal, their ions their ions turn their, but the means to say that their ions and the electrons in them are excited, and in this way they emit the flames of different colors. For example, barium salt gives a yellowy green color. Copper salt green, calcium salt, brick red, strontium, a crimson color, etc. It means to say that the mainly ions of metals are involved. Metals or non-metals, but ions of there are the main purpose of the colored flames. These are involved in the production of colored flames. Of metals and non-metals, there are ions that are responsible for their colored flames. Now flame test. What are flame tests? What is the theory behind the flame test? The theory behind the flame test is that the test involves inducing a sample of the element or compound to a hot, non-luminous flame and observing the color of the flame that results. The theory is that in the flame test, we introduce a sample of an element or a compound to a hot, non-luminous flame. We give them heat and then we observe the color of the flame that we obtained by heating that material. The idea of the test is that sample atom evaporates, and since they are hot, they emit light when being inflamed. And in this way, we identify the elements by their colored flames. Next, what is the chemistry? It is a qualitative test used to help determine the identity or possible identity of a metalloid ion in a compound. It is we can also say that it is a qualitative test. As I have told you earlier that the scientists are able to identify a compound, a metalloid ion in a compound. If we don't know about a compound or a metalloid ion in it, we can do its flame test, and in this way we are able to identify it. If the compound is placed in the flame of a gas burner, there may be a characteristic color given off that is visible to the naked eye, and in this way we can identify the element, metal, metalloid ion, etc., whatever it is. Next, what are the materials that are needed for the flame test? These are assorted metal salts, cotton swabs, watch glass, Bunsen burner, and water. These are the main materials that are required to do our flame test. Next, why do flames produce different colors? It is a main question that arises in our mind, that why do they produce different colors? And the chemistry is the behind this is that when you heat an atom, some of its electrons are excited to high energy levels. It is known, I have told you earlier. When an electron drops from one level to a lower energy level, it emits a quantum of energy. Whenever we give energy to an atom, its electrons jumps from the ground state to the high energy level. In this way, we provide them energy. But when an electron jumps from a higher level to a lower level, in this way, they emit energy in the form of light, which we can say that quantum of energy. It emits energy, it releases energy in the form of light. And the different mix of energy differences for each atom produces different light. And when they emit light of different energies, and the energy of the emitted light is depend upon the energy differences between the two energy levels from which it go into which. Means to say the energy differences between the lower energy level and the high energy level is the energy of the light that is emitted. Then different mixes of different energy are mixed up, and for each atom they produces different colors. Each metal gives a characteristic flame emission spectrum. This is also can be improvedly explained by the Gohans theory, which says that different elements have different flame colors because Their electrons have different allowed energy levels. We have studied it earlier in the 9th standard, 10th standard, and even in FSC, Bohr's theory. He says that in an atom, electrons revolve around the nucleus in a quantized energy levels. Those energies are quantized. Same thing is written here. The Bohr says that electrons exist only at certain allowed energy levels. When you heat an atom, some of its electrons are excited to higher energy levels. We give them energy, they got excited. From a ground state, they jump into the higher energy levels. When an electron drops from one level to a lower energy level, it emits a quantum of energy. As I have told you earlier, these are the same things. The wavelength or color of the light depends on the difference in the two energy levels. You can see only those transitions that correspond to a visible wavelength. It emits different wavelengths, different types of wavelengths, but we can only see those wavelengths which fall in on the spectrum in the region of the visible light. As we know, its wavelength is ranges from 350 nanometer to 780 nanometer. Only we can see those lights. Here we can see that when the electrons jump, when we give energy, since energy is given to the electron and from its ground state, it jump into a higher energy level. Electron observes sun's energy, and when it is get unexcited from high energy level, it goes to the lower energy level. Energy as color is released, and by the wavelength of these colors we identify, and these are the main reasons of the color change. Now, chemicals that make fire color change. Here are some examples of the here are some examples of the chemicals which are used and which gives different colors of fires. Here we can see that lithium chloride, and it gives red color. Sodium chloride gives yellow color. Potassium chloride gives purple color. Here is more some examples. We can say that every element give a different color, and the chemicals are responsible for their fire color changes. Here are some more examples. Here are the colors, and these are the chemicals which are used to produce these colors. When we need a white color, magnesium sulfate, purple potassium chloride, violet 1 part potassium nitrate. The other name for is saltpeter, and the third part is potassium sulfate. Green, copper sulfate or boric acid. Yellow or green, borax. Carmine, lithium chloride. Red, strontium chloride. Orange, calcium chloride. Yellow, sodium chloride or sodium carbonate. Blue, copper chloride. Now, what is the theory of the colored flame production? Abstract. The theories and attributes associated with the production of colored flames are presented. Particular attention is given to the flames containing strontium red, barium green, sodium yellow, and the copper green and blue. The thermal excitation of vaporized neutral atoms, molecules, and ions is correlated with the emission of atomic band and ionic spectra. We took some neutral atoms, some molecules and ions, and then we vaporized them. We give them heat, and when their thermal excitation occurs, these are correlated with the emission of the atomic band and ionic spectra. As we have know that we have atomic spectrum, band spectrum, and ionic spectrum. These values are compared with them, and these spectra are then tabulated. The color contribution of C-type chemiluminescence non-thermal excitation is briefly described in the theory of the colored production. Now, introduction. Colored flame production is beset with unusual problems. These problems are caused by the lack of choice in the available correlating material. The absorption of light by the atmosphere, the limits of discrimination by the human eye, and the chemistry and physics of the processes and substances involved. These are the main problems which were faced, which includes the choice of material, the human eye discrimination limits, the chemistry and physics of processes and the substances involved. To overcome the lack of choice problem, additional color creating materials can be made available by inorganic, organic, and metal organic chemical synthesis that in laboratory we have also created some artificial colors or artificial chemicals which were used to overcome the problem that is called the lack of the choice, that we artificially synthesize some color creating materials. In order to evaluate new materials, it is necessary to establish criteria by which the material may be judged. Now, what is the mechanism? Only a few of the more than 100 elements are used to impart a color to a pyrotechnic flame. Only more than 100 elements are used to impart a color. Therefore, there will be a need to create more color creating materials which were synthesized in laboratory artificially by the organic or inorganic materials. These are the strontium, red. These are naturally occurring. These are strontium red, medium green, 13, copper green or blue, and sodium yellow. Allen, who was the scientist, states that the lithium red, boron green, helium green, rubidium red, and cesium blue are also strong color producers, but that their use is not practical because of the cost, toxicity, or the nature of the compounds. He said that these are the naturally occurring, but their cost is very high, they are toxic, and their nature is not available, and that's why they cannot be used practically, although they are color creating, color producing, but instead they are strong color producers, but we cannot use them practically. All of these elements have certain properties and characteristics in common, which contribute to the colored light emissions. Fireworks. Fireworks are also an example of the colored flames fired. Colored fire. Colored fire is a common pyrotechnic effect used in stage production, fireworks, and by fire performers the world over. Generally, the color of a flame may be red, orange, blue, yellow, or white, and it is dominated by the black body radiation from soot and steam. When additional chemicals are added to the fuel burning, their atomic immune spectra can affect the frequencies of visible light radiation emitted. In other words, we can say that the flame appears in a different color depend upon the different chemical additives. Flame coloring is also a good way to demonstrate how fire changes when subject to heat and how they also change the matter around them. To color their flames, pyrotechnicians will generally use metal salts. Metal salts are generally used to make colored flames, or in other words, we can say that fireworks are generally made by using metal salts. Specific combinations of fuels and co-solvents are required in order to dissolve the necessary chemicals. when we added some chemical additives more artificially, and there are also required some combination of fuels and co-solvents to dissolve their necessary chemicals. Color enhancers, usually chlorine donors, are frequently added to. The most common of which is polyvinyl chloride. A practical use of colored file is the flame test, where metal cations are tested by placing the sample in a flame and analyzing the color to as I have told you earlier. Here are some of examples. Copper make a blue, firework, sodium made a golden yellow, barium made a green, strontium red, and titanium is a silver white. You can see that. Now, material details. Which are the materials that has been tested through the flame test and they give colored flames, and what are their properties and how they are used. First of all, we will talk about the barium strontium. Alan Hoover, the scientist, credited Hart as referring to the red flame as due to molecular bands in the red region caused by molecular strontium oxide and chloride and diluted with other lines and bands from incandescent particles. Hart also referred to the green flame as being due to bright blue bands from copper and barium chloride in the 4,000 to 5,000 and 5,000 to 5,500 angstrom region. More recent information leads to a slightly different explanation. Next, continue. Colored flame pyrotechnic composition contain organic binders and chlorinated organic molecules. As he have talked before, that the pyrotechnic composition contains organic binders which we artificially added to them, and also chlorinated organic molecules which were used for their chemicals to be dissolved. The combustion, which we can say that oxidation of these organic molecules provides the flame gases with the source of atomic and molecular hydrogen, neutral and negatively charged hydroxyl radicals, atomic and ionic chlorine and other materials. The low 57 calories per mole dissociation energy of molecular chlorine leads to the absence of molecular chlorine from the flame. Using barium as the example, metal several compositions can be expected. Here is an example. Here is a reaction by using the barium. Chlorine plus hydrogen plus OH gives out HCl plus OH. Then OH is reacted with the barium and barium oxide, and then chlorine plus barium gives out barium chloride. Now, alkali metals. The halogen effect with respect to the alkali metal is different from that just described for barium and strontium. Halogen affect differently with the alkali metals in contrast with the barium and strontium. Generally, because the desirable amine from the alkali metal is the atomic spectrum of the natural atoms, the addition of a halogen will not result in enhancement. The desired amine of the atomic spectrum will be substantially reduced because of the salt formation. When we add halogens in the alkali metals, we will not be able to enhance the color of the firework or any material which we are going to make. We cannot enhance their colors because when we halogen and alkalis are introduced, they react with each other and they form forms, and in this way they could not be able to enhance the colors. Now boron. When boron is added to a flame, the green color which results is due to predominantly to boron oxide. Some boron oxide is probably also formed, which emits mostly in the blue to ultraviolet. From thermodynamic data listed, it is concluded that the boron oxides are not only very likely to form delta F high, but also very stable, high dissociation energy. Except for the iodine, the boron halides also are identified with the high free energy of formation and dissociation energy. If the halide band spectrum were predominantly green in nature, the addition of a halide would be beneficial. On the contrary, however, boron fluoride has an undesirable yellow system, and bromine and boron chloride emit primarily in near ultraviolet. BF, we can say that boron fluoride has an undesirable yellow system, whereas bromine, and the boron chloride emit primarily in near ultraviolet color. If therefore a halogen other than iodine were introduced, a stable halide would form. This in turn would reduce the amount of the oxide present, which was radiating in the beneficial green wavelengths. The net result would be a shift towards the blue with a negative enhancement with respect to green. These are some journal informations about these materials. And the next one is thallium. To create bulk of the thallium in a flame is present as the free element. The green flame color is therefore due to the natural atomic spectrum. Oxide and hydroxide formation do not occur in the flame to any appreciable degree. The more electronegative halogen will form reasonably stable halides in the flame. These can be expected to emit band spectra. Helium fluoride, chloride, and bromide emit in the deep blue to near ultraviolet wavelength. These amines are of no particular value for green flame production. Thus, when a halogen is introduced, some stable halide forms. This in turn reduces the amount of the neutral amounts, which are radiating in the desired green lines. The net result is a shift toward the blue with a negative enhancement with respect to green. And the last one is copper. The great bulk of copper in a flame is present as the free atom with not more than 10% as copper oxide. Undesirable band spectrum for copper oxide in the orange region and weak bands in the green region. The free copper atoms emit a weak green line at 5105 angstrom. The composite of these amines would indicate a weak polluted greenish color. Contrary to this, copper when introduced into a flame exhibits a strong yellowish green color. This is attributed to a copper hydroxide molecular amine. Note that the copper hydroxide formation is recognized even in the absence of the halogens. In limited amounts, this is true also of barium, strontium, and lithium. Thank you so much. Here is my topic. I hope you can understand it. Thank you very much.